Once again, good morning everyone. I would invite Deepashri ma'am to start the session.
Good morning. Good morning, everyone. Am I audible?
Yes, ma'am, you are audible.
Okay. Just wait. Okay. So yesterday we started with periodic table, right? And we did a very brief introduction of what is a periodic table, why periodic table is important, and so on. So we all know that the we classification of anything is very important, right? Classification is very important because it actually helps us to get a knowledge of a specific element in near future within a very short period of time. I told you yesterday there are more than 100 elements in nature, but it is not always easy to get the idea of any particular element within a fraction of seconds. So that is the reason scholars, scientists from the time immemorial have been trying to classify the elements so that if someone wants to work with a particular element, obviously they will just know where that element is placed in the table or in the table of the classification, and accordingly they can predict some characteristics, right? So this was the basic definition or the basic idea for introduction of a periodic table. But how to introduce a periodic table? Nobody knew. Like someone, there are different theories we read how to introduce a periodic table, right? We know that the periodic table, they want that the periodic table should display all the chemical characteristics of the elements systematically. How? In order of the increasing atomic number, which is the number of the protons inside the nucleus. So that was their basic idea. They basically wanted to they basically wanted to infer any kind of the characteristics of any kind of the element. Okay. So Dauvergne started, and Dauvergne was the first person who introduced the concept, classified the periodic elements in a group of three, which he called triads. But obviously this concept failed because it failed to explain elements, all the elements, right? So Dauvernier's triad no longer came into use, so it was rejected. Octet's law was accepted by people by a short period of time, but he said to do it in the order of increasing atomic weights. And after doing this, he saw that every eighth element was very much similar with the first element. Okay, just like the musical note. But again, he saw it is not applicable for all the elements, and thus this law was rejected. Okay, so inert gases were not discovered till then. So eighth could be the metal or a non-metal during Newland's octet law. Then Lothermier's atomic volume card, where he just made a graph between atomic weight and the volume, and just classified the elements with similar properties on the basis of the graph. Then Mendeleev came. Mendeleev classified elements on the function of their atomic weights. So, can anyone tell me? Yesterday, I told you about groups and columns, groups, columns, rows. What are these? And periods. What is related to what? Groups are related with rows. Is it correct or not?
No, ma'am.
No. So what is the real answer? What is the correct answer?
Columns, ma'am.
Yeah. So what are periods then?
Rows.
Yeah. So rows are horizontal or columns are horizontal?
Rows are horizontal, ma'am.
Yeah. So periods are actually horizontal. So how many periods are there? And how?
7 periods,
Yeah, 7 periods. And how many columns?
18 columns.
18 columns.
Yeah, that is according to the new table, but according to the old table, there are 9 columns. Okay, just remember this. Periods remain same both in the uh, old and the new, 7. So we learned about this. What is the first period, second, third, and we know about the magic numbers. 2, 8, 8, 18, 18, 32. So 8, 8, 18. So these two comes and 2 and 32 are in the extremes. So this is something according to the old table. So which was proposed by Mendeleev himself. So we know that the first period is the shortest, second and third are short, fourth and fifth are long, sixth is the longest, and seventh is incomplete because Mendeleev believed. So Mendeleev was quite a person who could predict that, yeah, maybe some more elements could have been discovered. So Mendeleev just left space in his periodic table. That is his greatness. So Mendeleev just left some space in the periodic table, and this is what he then uh, left space in the periodic table, which was later came to be known as the inert gases. Okay, so this was something we learned. We know about different characteristics of the periods. Like I told you about the lanthanides, actinides. Right, we discussed about the third period elements. Also, apart from this, we discovered that previously valency used to increase, like the valencies were arranged in an increasing order. With respect to whom? With respect to oxygen. Like they form oxides, Na2O, MgO, Al2O3, and accordingly the valencies used to increase. We also know about the diagonal relationship, like lithium has similar characteristics with magnesium, beryllium with aluminum, boron with silicon, and so on. So these are the similar characteristics that has been observed, and this is referred to as the diagonal relationship, which exists between elements of the second and third periods. Okay. So Mendeleev, apart from this, we know about the normal elements and the transition elements. So can anyone tell me what is the normal element and what is the transition element with respect to 1, 2, 3, 4, 5, 6, 7, 8? Anyone?
D block will
Yes, eh?
D block elements are
Yes.
transition elements, ma'am.
Yes, exactly. So, 1A, 2A, 3A, 4A, these all are normal elements. 1B, 2B, 3B, 4B, 5B, 6B, 7B. These are the transition elements. And 1A, 1B, the elements in 1A, 1B are quite different. The only thing which is similar is their group number. And I told you, whatever the elements have the group number, that is their valency. Right? We told this. And we also know hydrogen is placed in both 1A and 7A. And generally, these are different characteristics of the group. And I told you, if you are remembering, if you are learning about any characteristics of an element with respect to period, just check for once what happens to the same characteristics in group. Okay, because you don't have to remember both. Mostly, if it is increasing along the period, it means it will be decreasing along the group. In very few cases, it will increase both in groups and periods. Okay. So This was another law which was proposed by Muesli. And mostly, according to him, physical chemical properties of the elements are the periodic functions of their atomic number. So if the elements, till now we were doing with atomic weights, but this is something about atomic number. If elements are arranged in order of their increasing atomic number after a regular interval, elements with similar properties are repeated, just like Dobrnius said. But Dobrnius said exactly the eighth element. But Moseley did not say the eighth element. He said that maybe. So after arranging the elements according to the increasing number of the atomic numbers, then there after some time the elements will show us similar characteristics with the already previously written elements. Okay, so that was what I mean to say, Moseley never said the eighth element will be similar, which Dobrnius said. So what was the long form on the Bohr's periodic table? Now, whatever we are learning, that is something we use in our day-to-day lives. So with better understanding of the role of the electrons in the properties of the elements and the development of the nature of the electrons in atom, a better understanding of the periodic properties of elements or the periodic table was possible. So what does this mean? Anyone wants to volunteer me? So with better understanding with the role of electrons in the properties of elements and the development of the nature of the electron in atoms, a better understanding of the periodic properties of the elements of the periodic table was possible. Why do you think this was said? Just anyone tell why this is said? Anyone, just say whatever you are thinking, just try to say. So no one. Okay, this means we all know that the atoms are composed of a nucleus. Okay, and the nucleus will have what? Protons and neutrons. Okay, and this nucleon and this nucleus, surrounding this nucleus will be present electrons. Better to say cloud of electrons. So the way the electrons are arranged in energy levels or in the orbitals, that actually defines the chemical properties of the element. Okay, so we know protons and neutrons are the constant part, but number of electrons vary. So as the number of the electrons vary, their chemical properties also vary. So that is the reason, with the difference in the number of the electron, with the variation of the chemical properties, there was a better understanding of the properties of element. So the periodic table is organized in such a way that elements with similar electron configuration are grouped together. This leads to observable patterns in different properties like reactivity, atomic size, ionization energy, electronegativity. Okay, and what was the Bohr model? The Bohr model is a simplified representation of an atom. He helped to visualize the arrangement of the electrons in an energy level. So this was quite important. This was the main contribution of the Bohr, of the scientist Bohr. So he made an atom in a simplified manner to make it understand to people. So by using this role of the electrons, later on the scientists were able to predict that with the variation of the electron, there is a variation in reactivity, ionization energy, electronegativity. What is reactivity? Like elements in the group tend to have similar chemical reactions. That is the reactivity. Ability to react, that is reactivity. Ionization energy is what? the energy which is required to remove an electron. That is the ionization energy. So if you have gone through the slides, you will know the ionization energy increases across a period and decreases down the group. Okay, so
Yes, ma'am.
why this happens? Because of the variation of the electrons. We know even if we are moving along the period or if we are moving down the group, there is a variation in the electron number, increasing, decreasing. So obviously the ionization energy is also varying. Electronegativity is the ability of an atom to attract the electrons towards itself. So ionization energy is energy required to remove the electron from its valence shell. Electronegativity is ability of an atom to attract the electron towards itself. Okay, so these are the things that actually vary. So Bohr was, so what is the summary of this slide? Bohr made a simplified atomic structure. Bohr made them visualize the arrangement of the electron in the energy levels. People understood that with the different number of the electrons, the reactivity, atomic size, ionization energy, electronegativity, different periodic trends vary along the period, along the group, and this gave them a better understanding of the periodic properties of the element. This made the periodic table even more scientific and even more understandable to the people. Okay. Okay, just wait for once. Is my screen visible?
Yes,
So
ma'am.
this
Yes,
long
sir.
form of periodic table is known as Bohr's periodic table. The long form of the periodic table offered the following advantages over Mendeleev's classification. Subgroup A, subgroup B elements are placed separately. See, I told you that subgroup A elements and subgroup B elements were quite different from each other. There was a clear difference between metals and non-metals, but they were placed in the same group, and that is the only similarity they have. But Bohr said no, they will be in different groups. And that is the reason in the modern form of the periodic table, you will be seeing 18 groups instead of 9. So the 9 elemental groups of group 8 have been placed in separate groups corresponding to D6, 7, 8 configuration. 14 lanthanides are not pushed together but are assigned a separate group for each lanthanon in the F block of the element. Okay, so what was this? Like the 14 lanthanides, they previously were pushed, no, they were not previously pushed together. But in near future, each lanthanon found their place in the F block. We will be doing F block, I guess, nearly at the end of the academic session. So that is a chapter where you do have to memorize a lot. So for now, just remember lanthanides are mostly in the F block elements. The uniform trivalent state of the lanthanons can be explained due to the availability of only 3 electrons in the outer high energy level. The differentiating electrons going to the inert chemically inert orbitals. So does anyone know what does this mean? What does this statement mean? Anyone wants to explain what does this statement mean? No one? So this statement, so lanthanides are a group of elements with atomic numbers 57 to 71. They all are metals that have similar properties. And the statement says that the lanthanoids have a uniform trivalent state because they have only 3 electrons in the outermost energy shell. These 3 electrons are called differentiating electrons. Differentiating electrons go to inner chemically inert orbitals. And this means that they are not involved in any kind of the chemical reaction. Chemical reaction means loss gain of the electrons. Nothing is happening here. So they are never involved in any kind of chemical reaction. Result of this is that all lanthanoids have same number of electrons in their outermost energy level. Okay, so is this part clear, whatever I explained so far? So the first part is clear or not? All the lanthanoids have the same number of the electrons in their outermost energy, and the lanthanoids have a uniform trivalent state because they have only 3 electrons in their outermost energy level. These 3 electrons are called the differentiating electrons. Differentiating electrons go to the inner chemically inert orbitals. So all the lanthanoids have the same number of the electrons in the outermost shell. So they are never involved in any kind of the chemical reaction. Okay, so this is something what I meant to say. Is this part clear to everyone? Respond.
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. So this uniform trivalent state of lanthanide is important. Why? So you can think that, ma'am, if they are not involved in any kind of chemical reaction, why are they even existing? Right. It is the uniform nature is the loss of any kind of chemical properties. Why? Because of their uniform trivalent state. But then why it is important? Can anyone tell me why it is important?
Which one, ma'am?
Like I told you, they are not involved in any kind of chemical reaction. Unlike most of the elements in the periodic table, they are not involved in any kind of chemical reaction. So why? And they are not involved in any kind of chemical reaction. Why? Because of their uniform trivalent state. So why is this uniform trivalent state is even important? Does anyone know the answer to this question?
Ma'am, is they are stable, that's why.
Uh,
Stability.
yeah, so that can be one of the reason, but it is not the major reason. When you will be learning the F block elements, you will realize that this uniform trivalent state of the lanthanoid is important because it makes them useful in variety of applications. Like lanthanoids are mostly used as lasers, magnets. Okay, so just imagine, even in medical imaging means like in MRIs and everything. Suppose MRI is done for what? For your brain. Okay. Suppose you are the patient, doctor has prescribed you to do an MRI. But the MRI, if the lanthanoids were reactive, you won't survive an MRI. Will you? No. So these are the things that actually help in imaging of the brain, but they don't react. So sometimes not reacting is a positive trait. So that is the reason lanthanoids are important. Uniform bivalence for the transition element is due to the presence of the outer NS2 electron, which makes them electropositive in nature. So what is this mean? Can anyone tell me what does this mean? What is NS2? What is that? So uniform bivalence for the transition element is due to presence of outer ns2 electron, which makes them electropositive in nature. So we know that the transition transition elements, we already know what are transition elements. So transition elements have this bivalent state, and lanthanides have a trivalent state. So the transition element often exhibit a bivalent state due to the presence of outer ns2 electron. These two electrons are relatively loosely held. So it makes them attracted to negative ions. And the loss of these two electrons result in a bivalent ion. Okay, so this is something which is being said. Transition elements have this bivalent state. And how this bivalent state exists? That the outermost shell has ns2 electron, and these two electrons are loosely held, so they can be lost easily. And that is the reason they get a positive, make them a bivalent ion. So the change from a highly electronegative to electropositive character through inert gas structure has been explained on the basis of long form of the periodic table. So this is the modern periodic table. Sorry, this is not the modern periodic table. This is something that was the old periodic table. See, lanthanides, actinides, they all are in the previous stages. Okay, so why I have given you this? This is simply given because, wait, because I told you yesterday to remember the elements. S block elements are in pink color. D block elements are this. P block elements are something like this. F block elements are in green, and so on. So just remember this. On the basis of the electronic class configuration, elements may be divided into 4 groups. This is the S block, this is the P block, this is the D block, and this is the F block. Okay, so is this part clear? Which are the S block, which are the P block, which are the D block, and which is the F block? So repeating it once again, see, S block. So this part and the extreme right part, S block. Then P block, then D block, and then F block. Okay, so we will be starting with the S block elements. So these are present in the left part of the periodic table. See, this is the S block. See, most of the things are in the left block, but hydrogen has been placed in both. So obviously, hydrogen is in 2 places. So obviously this part, it has also come, and this part. So this is mostly in the left. So these are present in the left part of the periodic table. These are 1A and 2A. See, both are AA. So 1 and group 2 elements, these are metals. In these elements, last electron fills in the s orbital. What does this mean? Electronic
It's S
configuration.
orbital.
Yeah, say.
It's S orbital, ma'am.
Yeah. So that may be correct, but can anyone tell me what does this mean in these elements? Last electron fills in the s orbital. What is this s orbital thing? Anyone just say fills in the s orbital. What does
NS2.
this mean?
Ma'am, I
Yeah.
think it's not S orbital, it's S orbital.
Yes. Why I'm telling you that in this element's last electron feels in the s orbital? Why I'm not saying it s orbital? Why? It will be s orbital. Okay, so just make the correction. It is s orbital. Does anyone know what is orbital? Anyone? It has been
Can
like
you
it
repeat?
has been a mistake in someone who made the slide. But what is orbital? I just wanted you all to know what is orbital. Sorbital, it's actually a sugar, okay,
A
sweetener.
alcohol, bro.
Yes,
It's
it is actually a type of carbohydrate. And this is s orbital. Okay, so there has been a mistake. That is the reason I am asking you repeatedly what is orbital, why it is said in this element's last electron feels in the orbital. What is orbital? So S block elements are elements in the periodic table and their last electron are in the s orbital of their outermost energy level. So orbital is something totally different. So to summarize, what can I say? That S block elements have their last electrons in the s orbital and they are present in the left part of the periodic table. 1A, 2A, these elements are present, basically group 1 and 2. They all are metals. Their electronic configuration is NS1 to 2. N means group 1, group 2. Sorry, N means 1 to 7. N is not the group number. Sorry, group number is 1 to 2 and their basic electronic configuration is NS1 to 2. So these p block elements. What is the p block element? See, wait. This is the p block element, the entire blue thing. So S are present in the extreme left, p are present in the extreme right. So these constitute the groups 3A to 7A and 0 groups. That is the groups 13 to 18 of the periodic table. Most of these elements are metalloids and non-metals, but some of them are metals also. S block elements, totally metals. P block elements, mixed, metalloids, non-metals. Sometimes metals also. So when we are learning about the p block elements, we will be learning this in extreme details, but okay. And again, this is not orbital. This is p orbital. So the last electron feels in p orbital of valence shell. Electronic configuration is it is to NP1. N here means 2 to 7. Yes, Akshaya, you want to say something? Yeah. So can you just please mute yourself? Akshay, maybe it was just a disturbance. The electronic configuration of the valence shell is NS2 NP1 to 6. Okay, just wait. NS2 NP1 6 is stable noble gas configuration. The electronic configuration of helium is 1s2. There no NP6 is present. Okay, so the basic electronic configuration of helium is 1s2. NS2 NP6 is stable noble gas configuration, and the electronic configuration of helium is 1s2. These are present in the middle part of the periodic table, D block elements. Iit-Jee, can you please mute yourself? D block elements. So D block elements are present in the center. We all know, for just few minutes before we saw where is the D. This is the D block element. Okay, in general, this is the D block element, and below is the F block element. Okay, so this is the D block element. As I was saying, that the D block elements are present in the middle part of the periodic table between S and P. S is the extreme left, P is the extreme right, and they contains 3B to 7B, 8, 1B, 2B. That is 3 to 2. That is groups of 3 to 2. If in exam they ask you which group, 3 to 12. If they ask you group number, that is according to the old table, that is 3B to 7B, 8, 1B, 2B. That is 1B, 2B, 3B to 7B, and 8. Okay, everything in B. These all are metals. Remember, only in the P block elements, there are non-metals, metalloids, and few metals. But S and D block elements, all are metals. And the last electron fills in N-1 d orbital. Okay? The outermost electronic configuration is N-1, D1 to 10, NS1 to 2. Here, N means 4 to 7. So, 4D, 6D, 7D, whenever you are seeing this, remember that is a D block element. There are 3 series of D block elements. We will be learning when we are learning about the D block elements. But for now, just remember there are 3 series of the D block elements. 3D series, 4D series, 5D series. 3D series is the Sc to zinc. 4D series is Y to CD. And 5D series is the lanthanum HF to Hg mercury. Okay, so this something you have to remember. So 3D series, 4D series, 5D series. Why they are special? What are their in general characteristics? You will be learning this in near future. But for now, just remember these are the important things. F block elements. F block elements we already discussed. Some that the F block elements are actually the lanthanides. But what are these F block elements? These are placed separately below the main periodic table. These are mainly related to 3B, that is group 3 of the periodic table. There are 2 series of F block elements, 4F, 5F. There was 3D, 4D, 5D. Here only 4F and 5F. 4F is the 14 lanthanides, 5F is the 14 actinides. Okay, 14 lanthanides means cesium to lutetium, and 14 actinides is thorium to LR, which is 190 to 158 to 71. So these are actually F block elements. So the last electron fills in N-2 F orbital. And their outer electronic configuration is this: F, S, P, D, NS2. So N can be 6 or 7. So N-2 F1 to 14, N-1 S2, N-1 P6, N-1 D0 to 1, NS2. These are the different F block elements. So what are the Bohr's classification of the elements? On the basis of the electronic configuration of the incomplete shells, elements are classified into 5 major categories. Okay. Just wait. Is the slide moving? inert these are the inert gases, representative elements, transition elements, inner transition elements, transuranium elements. So all this classification is convenient for understanding the chemical properties of the element. It overlooks the specific properties of the individual elements. See, Bohr made a basic classification of the elements. What are inert gases? What are representative elements? What are transition elements? What are inner transition elements? What are transuranium elements? But he never mentioned any specific characteristic, such as we all know what are the inert gases. So name the inert gases. Anyone? Anyone volunteer me with naming the inert gases?
Novel gases.
Yeah.
Neon.
Neon, argon, krypton, xenon, radon. So neon has some specific characteristic which is different from xenon. That is why neon is neon, xenon is xenon, radon is radon, argon is argon. Right? He never mentioned that specific characteristic. Yes, all the inert gases have specific properties. Very true. But he never mentioned the specific chemical properties. Apart from this, there are representative elements, transition elements, inner transition elements, transuranium elements. So previously, does anyone know what are these? Does anyone know what are representative, transition, inner transition, transuranium?
No, I just know two of them.
Yeah, but still you can think what are the transition elements we have read.
D block elements.
See, inert gases we all know. Representative elements means these are elements that represent the typical properties of their respective groups in the periodic table. Okay, like hydrogen, carbon, oxygen, nitrogen, sodium, chlorine, magnesium, they all represent the carbon represent the typical properties of the group 6, I guess. So group 6 element is carbon. We say like carbon family, oxygen family, nitrogen family, right? So these are the representative elements. They will be representing the typical properties of their respective groups. Transition elements, these are the elements that fill their d orbital as their outer electron shells are filled. Okay, so these are typically the metals that often exhibit multiple oxidation states like iron, copper, zinc, silver, gold, platinum. These are the transition elements. Inner transition elements means lanthanum, cerium, neodymium, uranium, plutonium, americium, I guess. So these elements fill their f orbitals as their outer shells are filled. So transition elements fill their d orbital, inner transition elements fill their f orbital. Transuranium elements, these are the elements with atomic number greater than 92. Okay, so these all are basically radioactive and they are produced artificially in nuclear reactors or particular particle accelerators. Like you all know this, like curium, californium, plutonium, neptunium. So these are the transuranium elements. Okay. So inert gases, s and p orbitals of the outermost shell of these elements are completely filled. Outermost electronic configuration is ns to np6, except for helium. Helium just have 1s2. They don't have np6, that part. So helium just has ns2, that is 1s2. representative or normal elements. Outermost shell of this element is incomplete. The number of the electrons in the outermost shell is less than 8. Inner shells are complete. S and P block elements, except the inner gases, are normal or representative elements. Transition elements. Last two elements of these elements, namely outermost and penultimate shells, are incomplete. Last shell contains 1 or 2 electrons, and the penultimate means just before the last shell. That may contain more than 8 up to 18 electron, and their outer electronic configuration is this. So they are mostly the D block elements, iron and so on. So according to the latest definition of the transition elements, those elements which have partly filled d orbital in the neutral state or in any stable oxidation states are called the transition elements. According to this definition, zinc, cadmium, mercury are d block elements, but not transition elements, because these elements have D10 configuration in neutral as well as in stable +2 oxidation state. So just now what I have explained a few minutes before, that they have partly filled d orbitals in the neutral state or in the any kind of the oxidation state. So zinc, cadmium, mercury, they are D block elements, but not transition elements. Why? Because they have a filled D10 configuration in neutral as well as in +2 oxidation states. And transition elements have partly filled d orbitals, but they have the completely filled d orbitals. And that is the reason they are not considered to be the transition elements, even though they are the D block elements like zinc, cadmium, mercury. Remember this exception. Okay, so what we have learned today, we have firstly started discussing with the periodic table, why the periodic table was necessary, and we discussed the history, Daubeney's triad, then Newland's octet law, then Lothermius atomic volume curve, then Mendeleev's periodic law, then characteristics of the periods. So apart from this, we know that previously they used to follow uh, they used to consider oxygen for their valency. We also know this. Apart from this, we know the groups. What are groups? Previously, 1A, 1B, 2A, 2B, this was present. But in the modern periodic table, they have been separated totally and completely. And then the hydrogen is placed in both 1A and 7A groups. Then the properties and the characteristics of the elements, they vary greatly along the periods and along the groups. We know about the Moseley. Moseley said that Moseley was the first person who gave that idea, right? And then Bohr made a simplified atomic model that actually help people to understand that the electrons vary for elements to element. And with the loss or gain of electron, chemical characteristics of the elements vary. And as the chemical characteristics of the elements vary, obviously we can say that different elements are different with respect to chemical nature because of the specific electronic configuration that they possess. Okay, so that was the Bohr's idea. That was what Bohr tried to explain to people, and a long form of periodic table came. And subgroup A, subgroup B is clearly differentiated. Then 9 groups, including 7, have been placed in separate corresponding to 6, 7, 8. Lanthanides, actinides, they have been included in the F block elements. Then lanthanides, I discussed that they have a trivalent state, and the differentiating electron goes to the Inert orbital. What are these differentiating electrons? The trivalent electrons, trivalent state of the lanthanides. These are the differentiating electrons. They go inside the inert orbitals. And that is the reason lanthanides never react. They are chemically inert. They never react. And that is why they are used as fridge magnet, any kind of magnets, or for imaging techniques, like in medicine, MRI. So that is the main use for the lanthanides. Uniform bivalence for the transition element is due to the presence of outer NS2 electron, which makes them more electropositive in nature. Actually, the electrons are present in a low state, and that is why the two electrons can be lost easily, which makes them electropositive in nature. So transition element has a bivalent state. Lanthanons have a trivalent state. Change from a highly electropositive to highly electronegative character through the inert gases structure has been explained through the form of this periodic table. We know what is the S block element, P block element, D block element, F block element. We know what is the basic characteristics of the S block element, and we also pointed out a mistake that it is not s orbital, it is S orbital. S block element are all the metals. P block element can be metal, can be. So maybe metal, may not be metals, and metalloids are actually present. Group 13 to 18, or according to the old periodic table, 3A to 7A, and 0 groups. Most of these elements are metalloids, non-metal, but some of them metals too. Last electron fills the p orbital, and we have to remember the general electronic configuration. Exception is helium. Helium does not have NP6, that part. D block elements are also metal. So S block and D block all are metals. P block non-metals are present. And the last electron fills N-1 d orbital. General electronic configuration is this. And there are 3 series. We will be learning about the series in extreme detail when we are discussing about the D block elements in the D block element chapter. 3D series, 4D series, 5D series. F block elements placed separately below the main periodic table, which was in the previous table's place, but in the long form of the periodic table also you can see. These are actually the 4F, 5F series, and 4F, 5F series means 4F means lanthanides, 5F is the actinides. Last electron fills N-2 F orbital. Outermost electronic configuration is this. This is something you have to remember. Bohr's classification is on the basis of the electronic configuration of the incomplete shell. Elements are of 5 categories: inert gases, representative elements, transition elements, inner transition, transuranium. Okay. So inert gases are S and the p orbital of the outermost elements are completely free. These are the noble gases. These are the ideal people of the periodic table. All the elements want to be like this inert gases, stable, filled orbitals, and so on. So chemically inert. So filled orbital means they will not lose or gain any electrons. So they have stability in life. Everyone likes stability in their lives. So inert gases are like that government job employees. Everyone is looking upon them. Everyone wants to be like the inert gases. Representative or normal elements, then transition elements, and this is the modern definition for the transition elements, that zinc, cadmium, mercury, though they are the d block elements, but they have filled d orbitals. That is the reason they can't be considered as the transition element. So this, and apart from this, we learned about transuranium element. Transuranium elements are elements above atomic number 92. So does anyone has any doubt?
No, ma'am.
No, ma'am.
Does anyone have any doubt? No one, no doubts? Everything is clear?
Yes, ma'am.
Okay. So, ma'am, this was all from my part. Hello, ma'am. This was from my part. Ma'am, are you there? Yeah, actually, sir will send you all the notes. Okay. Okay then. Bye.
Bye, ma'am.
Bye, ma'am.
Yes, students, now you can join the next link, 6 to